in this chart, I want to talk about Huffman codes compared with the Shannon codes. So for x is a binary, that x equal to 1 with a probability 2 to the minus 10, x equal to 0 with a probability 1 minus 2 to the power of this should be 10. Okay, so this should be 10. Okay, and the Shannon code for x is equal to 1 is log 2 of inverse of this probability, which is 2 to the power of 10. So for x is equal to 1, we have a binary code of length 10. And when x is equal to 0, we have a binary code of length 1. So that's the Shannon code. And if I use Huffman code, since I have only 2 items, the length is 1. So basically, I can assign x equal to 0 to be bit 0, x equal to 0 to be 1, or vice versa. So the Huffman code have 2 code words. Each has a code word of length 1. So the expected length of Huffman code is 1. And the Shannon code, what is the expected length? So in this particular case, length 10 that occurs with probability of 2 to the minus 10 plus length 1 occurs with 1 minus 2 to the minus 10. So what is the expected length? This is close to 1, right? So Shannon code and Huffman code are very close. So a code word with for infrequent symbols in Shannon code is much longer than in an optimal code. Okay, but this does not mean that a code word in an optimal code is always shorter than those in the Shannon code. So if this can be entertained by taking this example. So when x is has a 4 element in the alphabet, and each occurs with these probabilities, then we can construct 2 kinds of Huffman trees, which results in these length collections. And using Shannon code, I could have code word length of, this one is smaller than 1 over 4, so the length is 2. This one is again smaller than 1 over 3, so length is 2. This one is exactly 2, and this one is smaller than 1 over 16. I mean, this one is larger than, sorry. So 1 over 3 is larger than 1 over 4. So it is 2, length is 2. And this one is exactly the same as 2 to the minus 2. So it is 2. This one is larger than 1 over 16. So the length of a code word for that case is 4. So this is Shannon length. And then we can talk about 2 different Huffman trees for this distribution. For example, let's say third, 1/4, 1 over 12. We could add these 2. So 1 over 4 is 3 over 12. So this one is 4 over 12, which is 1/3, right? 1/3. Then we could add these 2 first and then add these later. And then we can assign 0 for up, down for 1. In this particular case, The first item is 1, the second item is 1, 0, the third item is 1, 1, 0, fourth item is 1, 1, 1. So in this particular case, the length is 1, 2, 3, 3. So that is this case, 1, 2, 3, 3. And we could have different ones. In this particular case, we could, let's see, add these two, and that becomes 2/3, and as these two. And we can assign 0 for up and 1 for down, and we can come up with different code words for this tree, which is what? So first item is up and up, up and down, down up, down down. So this is the collection of code words for this tree, which has length 2 for each case. So that is this. And when I compare the Shannon length, which is 2, 2, 2, 4, and so Shannon code with here infrequent symbol is much longer than in optimal code. This is in general in typical case, but it has some case that that is violated, that is in violation. So for example, in this particular case, 1/4, this item, in Huffman code, it is represented with 3 bits, but here in this Shannon code, it is represented with 2 bits. Okay, so this relation is not always holds. So it depends on a particular case. So it is a case-by-case scenario. So so that's what we need to remember. Okay. So note that the length of the third code word is 3 and 2 for the second Huffman code and Shannon code respectively. So I think I have to code respectively. So that's that. And that's the end of Huffman code.